Hi, good day. My name is Lawrence Liu. I'm a member of the RD team here at PUF Security, and today I'll be talking about PUF-based solutions for supply chain protection. We'll start with the agenda. Just a brief corporate overview, how PUF can solve modern supply chain issues, and an introduction of NeoPUF and PUF-based solutions. And starting again with the corporate overview of PUF Security and eMemory. eMemory was founded in the year 2000. It's a pure-play IP company, and the majority of employees are IP developers. For 11 straight years, we've been the proud recipients of TSMC's IP Partner of the Year Award for embedded memories. And here we have PUF Security. PUF Security was created in the year 2019 to promote PUF-based security IPs using eMemory's IPs such as NeoFuse and NeoPUF. Now we come to the main topic of today's talk, which is PUF for solving modern supply chain issues. So first, let's take a step back and look at the concept of identity. Identity is important to hardware security because without identity, it's very hard to have security. Now, traditionally, this has been done through the use of a hardware secure module. The hardware secure module is used to inject the key or write the key into each device. And this is done in a secure cleanroom environment. The secure cleanroom environment is used because to prevent the malicious cloning, malicious assignment, or other attacks upon the ID of a device. This process with the HSM and secure cleanroom is known as external key provisioning. That is, the key comes from an external source and is injected or written into the device. Because of the costs associated with maintaining a cleanroom environment, there's been interest in looking for ways to do internal key provisioning. This leads us to the concept of a PUF, also known as a physically unclonable function. Also known as an inborn hardware fingerprint, a PUF takes the inherent physical differences between each die and amplifies that into a readable pattern of random numbers. Besides being a source of random numbers, a PUF will have the following properties, such as physical unclonability. Physical unclonability refers to the fact that if a PUF is copied, if the structure of the PUF is copied, the values of the PUF inside will not be copied. So if a hacker was trying to steal an ID by copying a PUF, then the ID would not be cloned over. Secondly is evaluability. Evaluability, also known as measurability, refers to the fact that a set of standard metrics should be used to be able to compare different methods of PUF implementations. Third is uniqueness. A PUF value should be unique. No two PUF values should be the same, just as no two IDs should be the same. And finally, fourth is reliability. A PUF should be reliable for the lifetime of its usage, from day zero to the end of lifetime. So now we come back to the issue of the modern supply chain, shown here in a simple diagram, from production or design engineering through the device level, module assembly, and in-field use. Originally, the modern supply chain could have been all housed under one roof, at least in the same time zone. But now, the supply chain has been stretched globally because of tighter and tighter margins that businesses must face. As a result, since watching over a long chain is tough, vulnerabilities appear when oversight is weak, such as the case with the recent SolarWinds attack. SolarWinds, the software update server, was targeted by hackers to release malware in official updates. So this can be considered an in-field attack. An earlier example was from Supermicro. Supermicro had motherboards that were found to have some extra chips installed. These extra chips were actually sending beacons back to China, and then malware was being installed on these boards. So this could be considered a module or product assembly stage of attack. Besides these attacks, supply chains will face other issues such as reverse engineering of designs, overproduction, leading to counterfeit goods being sold on the gray market, and finally, software attacks or hacks. So let's continue by looking at the stages one by one. Here we have the first stage, production or design engineering. At the first stage of the supply chain, certain decisions must be made, in particular in regards to security, such as the example we mentioned before, in terms of identity. Decisions need to be made such as how to assign identity, such as either using key provisioning internally or externally. Again, as a review, previously we talked about the external key provisioning using a hardware secure module, HSM, injecting a key into the device, and therefore giving it identity. And also we talked about the alternative, using a PUF. A PUF-based internal key provisioning system would do this all internally and yield the same result with a unique ID in the device. But the difference here is a PUF device yields two main benefits. The first is that the key provisioning is done internally, so there's no chance of key leakage. And secondly, the clean room itself, the clean room and the hardware secure module, the costs of that are eliminated by using an internal key provisioning system. Moving on to the next stage, at the device level, companies may face a problem of overproduction. Overproduced goods may end up in counterfeit or unauthorized clones of a company's products. Without a formal factory audit in place, these products may end up on the gray market. As an alternative, PUF-based solutions introduce the idea of installing an activation code. Using an activation tool and the device's inherent hardware unique key, an activation code may be written into authorized devices. For overproduced parts or counterfeit parts, without an ID or without the activation tool, the activation code cannot be written. Later on, when this pairing is checked, when the HUK and the AC is checked to see if it's a match, authorized parts are activated. Whereas for parts without an ID or without an activation code, they are disabled, thereby solving the problem of overproduction. Moving on to the last stages of the diagram, we come to asset protection. A company may spend a long amount of time developing the soft assets for their product, such as software, firmware, or trained AI models. Here seen stored in a flash. If these soft assets are stored as plain text, then it is easy for anyone to come and copy their soft assets. For a PUF-based solution, PUFs, besides offering a hardware unique key, they can also offer a local encryption key, such that the contents of the flash can be encrypted and protected from theft. All right, summing up this section, we come back to the diagram of the supply chain, showing the production, device level, assembly, and field use stages, and the various problems associated with the stages, such as reverse engineering, overproduction, counterfeit goods, and hacked and cloned firmware software. And now we just briefly talk about the benefits of adding a PUF and PUF-based solutions to your supply chain, such as a low-cost HUK using internal key provisioning with a PUF, anti-reverse engineering, since a PUF can't be cloned, anti-overproduction using the activation checking code, firmware software counterfeit protection using the soft asset protection of encryption with a local key derived from the PUF. And finally, this last point of hardware root of trust. We'll get into that in the next section when we introduce NeoPUF and PUF-based solutions from eMemory and PUF Security. All right, thanks for making it to the last section of the talk today, where I introduced NeoPUF and PUF-based solutions from eMemory and PUF Security. Okay, so first up is eMemory's NeoPUF. Introduced in 2018 in a paper at the ISIS-CC conference, winning Outstanding Far East paper that year, NeoPUF is a PUF based on the mechanism of quantum tunneling. Quantum tunneling allows the different random distribution of gate oxide defects that occur naturally after a wafer is processed in a pair of transistors here, to determine a random 0 or 1 bit value. During the process of enrollment, when random values are assigned to a PUF array, a high voltage is applied across both pairs of transistors that make up one cell of the quantum tunneling PUF, and this is considered one cell. Now, due to the difference in microstructures of the two gate oxides, a current path will start to develop in one of the transistors, such as either in the left or the right. As the current path develops in the one transistor, the voltage across the pair will drop so that a current path can only develop in one of the transistors, such as if the current path starts to develop here in the left, then there won't be developed one in the right. So at this point, we can assign a bit value for this puff cell. For example, a 0 can be assigned when the current path is on the left, and a 1 can be assigned when the current path is on the right. After repeated experiments and measurements performed over a wide range of process nodes and operating conditions, it was found that an array of such pairs of transistors yields almost perfect 50-50 0 and 1 bit distribution. And this is what we call NeoPUF, an array of these pairs of transistors. And this 50% measured value for NeoPUF matches nearly with the ideal 50% value that an ideal puff should have. So if we take a look at the Hamming weight, ideally we should get a 50%, and NeoPUF measures a 50%. And if we compare that to an SRAM puff, we note that the range is quite wide. It's like 40% to 65%. So in addition to measuring the 0 and 1 bit distribution using Hamming weight, we have these other metrics that are used to compare NeoPUF with what our ideal vision of a puff should look like, as well as compared to SRAM puffs. So moving on, we have Hamming distance here. Hamming distance measuring the uniqueness of puff values between different die. It should have a ideal value of 50%, which is what NeoPUF has. And then if we look at SRAM puff, we see it varies from 45 to 50%. Number 3, we have the bit error rate, which measures the robustness. It shows how stable and reliable the puff values are after multiple reads over different PVT conditions, process, voltage, and temperature. And ideally, a puff should have 0% error rate, reliably performing over a wide range of conditions and processes. And NeoPUF has been demonstrated to have a 0% bit error rate over the various PVTs that we measured. And this is using raw data. Raw meaning no post-read data processing. And contrast that with SRAM puff. Without error correction, an SRAM puff will have a bit error rate anywhere from 1.5 to about 20%. And then fourth, we talk about reverse engineering. And that's to check if puff values can be determined through other means, such as through visual checking using an electron microscope or analyzing leftover charges through the phenomena of data remnants. Now, ideally, a puff should not allow any of its values to be determined through any other means of access besides a normal read. And that's one of NeoPUF's strengths. Just as an ideal puff should be untraceable, unable to be reverse engineered their data values, NeoPUF is the same way. On the other hand, since a SRAM puff depends on an SRAM memory cell structure, the SRAM puff is vulnerable to the same types of attacks that affect SRAMs as well, namely determining the values of the SRAM through laser probing or remnant charges stored in the SRAM cell even after the puff has been powered off. And that's why we wrote conditional here for SRAM puff. It is vulnerable to certain attacks. Fifth, we move on to yield and reliability. Yield and reliability talks about how manufacturable a puff is. Ideally, a puff should be able to be produced in the preferred fab of the user's choice. Leveraging eMemory's relationships with all major foundries over its 20-plus years in business, NeoPUF has already been qualified or will be qualified in all process nodes down to as small as 5 nanometer FinFET technology. Now contrast that with the SRAM puff, which is quite sensitive when migrating from process to process, as the error correction on an SRAM puff will need to be adjusted each time you migrate process nodes. Now this limitation and flexibility for the user for the choice of fabs is why we call it a lack of flexibility for the SRAM puff. And finally, especially important for aerospace or defense applications is radiation resistance. Ideally, a PUF should not be affected by radiation. NeoPUF has been found to be radiation insensitive. Unfortunately, because an SRAM PUF is dependent on the working characteristics of its underlying SRAM memory cell, it is more susceptible to radiation, particularly in the form of soft errors being generated when it is exposed to radiation. So that's a general overview of ideal PUFs, NeoPUFs, and SRAM PUFs. Moving on, we can see how PUF Security integrates the technology of NeoPUF into their PUF-based security products. PUF Security has taken eMemory's technology, such as NeoPUF and NeoFuse, which is eMemory's OTP, and created two hardware roots of trust, one called PUF-RT and one called PUF-IoT. Design philosophies between these two roots of trust is the same. Taking the OTP at the center and protecting it with entropy from the PUF and TRNG, and finally wrapping it in an anti-tamper shell, we create these two roots of trust. The only difference here being PUF-IoT includes cryptographic engines to enable more flexible security protocol implementations. Next, we'll take a more detailed look at PUF-RT here. In a diagram of PUF-RT, it shows 5 blocks. PRTC is a standard APB bus interface along with access control. PUF-TRNG is a true random number generator. PUF-UID derives a hardware unique key or a unique ID from the PUF values of NeoPUF. And PUF key storage is a self-encryption module to protect the data stored in the OTP here, in the hard macro, which contains both the OTP and PUF. Moving on, we also see the hard macro here in this diagram, showing the division between the hard macro and the digital RTL portion of PUF-RT. And on the right here, this table shows the different anti-tampering features that are present in all PUF-RT designs to protect from invasive attacks, semi-invasive attacks, and non-invasive attacks. Moving on to use cases for PUF-RT. PUF-RT has 2 configurations, one a single bus and the second a dual bus. For the single bus, PUF-RT is made to be hooked onto the main bus here. And for the dual bus case, the main bus is still utilized, but then a second private data bus can be used for more secure passage of sensitive data, such as private keys. So on the next slide here, we have the family of PUF-RT solutions. First showing the 2 configurations of single APB and dual APB here. This family of solutions based on PUF-RT consists of a common set of hardware root of trust features, and then additional add-on modules to offer solutions for various problems that a company might face, such as key management. We have PUF-KeyGen. For anti-overproduction, as mentioned in the previous section, there's PUF-SIG. For protection of soft assets in an external flash, we have PUF-ENC. And finally, for embedded flash solutions, we have PUF-Flash, offering RC6 encryption. But if these features aren't enough for customers, we also offer PUF-IoT, the PUF-RT-based secure coprocessor. Taking PUF-RT as a base, noting these 3 lower layers, we add on additional cryptographic engines, such as for key management, message authentication, elliptical curve cryptography. With the addition of such crypto engines, we can offer more complex security protocol support, such as secure boot, transport layer security, and key management. So in addition to the APB interface, as seen on the PUF-RT in the PRTC, it is called PITC here for PUF-IoT. And then for additional data throughput, we offer a direct memory access module here, which can be hooked up onto a faster AXI or AHB bus. So again, as with PUF-RT, PUF-IoT has been made to hook up onto the system bus. In this diagram, we just want to emphasize the advantages of Puff IoT as an integrated solution. As an integrated solution, if there is any sensitive data, such as private keys, that need to be processed, all such data can be safely processed within the boundaries of Puff IoT. In contrast, on the right-hand side, we see what happens if crypto engines need to be hooked up onto the main bus. In this case, if we have private key data that needs to be sent from, say, the CPU to the ECC, then it can only be sent on the main bus. And if it's on the main bus, the more views that it can see, the higher the risk of key leakage. So just like with PuffRT, Puff IoT also has a family of solutions based on Puff IoT. Starting from the basis of PuffRT, with its hardware root of trust, the addition of cryptographic engines make up Puff IoT. And then on top of that, different accessories are added to offer security solutions for customers, such as Puff XIP for NOR flash protection, including execution in place. Puff EF, again, for embedded flash protection. And Puff ENC, again, talking about soft asset protection. So that was a brief overview of PuffRT and Puff IoT solutions from eMemory and Puff Security. But listening to our designs is probably not as much fun as playing with them, which is why we have IPGo, a free way to test out the PuffRT and Puff IoT solutions. You can go to this website here and download all the details for this program. Free to use, risk-free, and play as much as you want. Thanks a lot for your time today. I hope you at least took away one piece of useful information. I just want to leave you with the last slide showing our two contacts. You can talk to either Mr. Dave Sinofsky or Mr. Akin Wang, depending if you're in the US or Taiwan or whichever location is more convenient. And their English is just as good as mine. So thanks again, and have a great day. Bye-bye.